Now I want to finish this handout by talking about why it's so imperative for us to understand a bit about test functions. We certainly needed more than just the zero function for this to make any sense, but I want to remind everybody why it was so crucial, why it was a big unfinished piece of business to understand something about test functions. And that's why, do distributions even make sense as generalized functions? What are these gadgets? We've been thinking of them as things that include functions and more, like deltas and delta primes and things like that. But that's not going to make any sense if the same two function, if two different functions rather, represent the same distribution. And let's just test it on a very special case. Suppose I have a function in the ordinary way. I think of it as a distribution. In other words, I look at this operation from test functions to R. Suppose that this always gives me 0. I better have that f is essentially the zero function as well. If I had a non-zero function that never gave me anything interesting on a test function, then I would be losing information when I thought of that function as a distribution. So one fancy way to say that is I want to show that this natural inclusion, we really defined a set mapping from ordinary functions into the set of distributions. And we still haven't completely nailed down the precise definition, but we will soon, I promise. I want to show that this is one-to-one. Is this 1 to 1? Or do I have a real or huge problem that I can't tell some functions apart from the zero function once I think of them as distributions? Okay, so that's the motivation for what we're doing in 4a. I have f, an ordinary function, and I'm going to assume it's continuous. Now, not all of our functions that we want to turn into distributions are continuous, but we have to have some assumption because we know that we can redefine functions on finite sets of points, and possibly rather bigger than finite sets of points, and not change their interpretation as a distribution. So there is a sense in which that hope of that mapping being one-to-one is a little bit fake. But let's at least do it for continuous functions, and then that's the simplest setting, okay? And what we're going to assume is that f kills every test function. So when you think of it as a distribution, it's equal to 0. I want to show that f is identically the 0 function. And we'll actually show it by contradiction. Let's assume, which might be more natural to think of anyway, assume that f of some x naught is not equal to 0. And I want to show that f on phi is not equal to 0 for some phi. And the task will be to construct a phi that guarantees that and to make sure that that's true, that's not equal to 0. And without loss of generality, I'm going to assume it's greater than 0. The two cases are pretty obviously equal or equivalent. Okay, so I'd like to show this. And in fact, I'm going to show that I can create a test function that's greater than 0. So how do we use the fact that f is continuous? The point is that if we didn't have f being continuous, this wouldn't tell us much. If all I know is it blips up to here, it could very well be 0 everywhere, but at that point, and that's the kind of function that integrates up against every phi to be 0. The point is that if it's continuous, it drags up all the nearby values with it. And that is the kind of function that if I pick a test function that looks actually rather like that, something that's also guaranteed to be positive in this interval, then I'm going to get a non-zero number. So it's a good example of using continuity really carefully. So this has some value. We know that this is f of x naught, and we know that that's greater than 0. And we want to make precise the idea that there's some values around it that are well away from 0. To make sure that we really get a nice chunky integral when we integrate it with our chosen function phi. So what's a good bound away from 0? Well, there's only one number in this problem, f of x naught. Let's try to make sure that a fair number of these guys, that some neighborhood of x naught actually sends values to values of f that are bigger than f of x naught over 2. So we just have to remember the definition of continuity. We are assuming that f is continuous. We really just need to assume it's continuous at that one point. Okay, and so this is connecting, it's going to test a little bit how familiar you are with like epsilons and deltas. Okay, so here's the definition of continuity at a point. That means that for every epsilon greater than 0, okay, so that's every like wiggle room error tolerance in the output, there is some delta greater than 0. So I challenge you to make sure your output is not too different from f of x naught, but I allow you, and what I want is I allow you a certain error tolerance here, and you need to make sure you can guarantee the values are in this error tolerance with some tolerance on the input. So that there's some delta greater than 0 such that if x minus x naught is less than delta for all x, let's say for all x, let's emphasize this, for all x with this property, then f of x minus f of x naught is less than epsilon. It's often phrased as like a challenge and response. I challenge, or somebody challenges me with an epsilon. They say I need the values of x naught, the values of f to be within 10 to the minus 6th of this guy. Can you guarantee that that's true? And I get to pick the delta. I get to say, well, I'm going to have to restrain the x's to be very, very close to x naught. But I'm not allowed to just say, well, x naught works. I'm supposed to say there's some error tolerance, but I'm allowed to make it as small as possible, as small as I want, so that when the inputs are within that tolerance, the outputs are within the tolerance that I was challenged with. Okay, so what I'm just going to do is I'm going to say, oh, every time I know this is true, no matter what the challenge is, I'm going to say let epsilon equal f of x naught over 2. Remember, for simplicity, f of x naught was greater than 0, so that's totally illegal, greater than an epsilon that's greater than 0, okay? And so now there is some delta, and I never even going to need to know what that delta is, just it's greater than 0, okay? Such that this is true, okay? And now this is now less than f of x naught over 2, okay? And if I'm if I'm within half of f of x naught to f of x naught in particular, I'm up here, I'm away from 0. So in other words, for all these x, then I can say that f of x, which after all is f of x naught plus f of x minus f of x naught. Actually, let me switch that a little bit. It's going to be that minus f of x naught minus f of x. Okay. That's going to be greater. I know this is a small number. From here, it's smaller than f of x naught over 2. So that's going to be greater than this. Oh, hey, and that's f of x naught over 2. So exactly what just was in the picture. If I'm close to this level by this much, I cannot be below half that level. That's excluded from me. Okay, so this is the crucial thing, that I've got a little interval of width 2 delta where f of x is known to be big. It's no longer just known to be positive at one single point, which would be useless. It's known to be positive on an interval. All right, so now we draw the picture again. Okay, so here's f. I don't really know much about it, but it's continuous, and I know that there's this interval x naught plus delta and x naught minus delta where it's above a certain value, namely f of x naught over 2, but the main thing is it's just a known positive value. So now I'm going to come in with a step function, a smooth step function, and this is where we absolutely needed that smooth step function. And I'm going to go ahead and I'm going to not even have it turn on until I'm in the region where I have good control. And then I'm going to make it come up to 1. Then I'll have it turn off and then be dead out here, because I don't know what happens outside of this x naught minus delta, x naught plus delta. It could go negative, it could get huge crazy values, there could be some cancellations, but if I'm not going to do anything with the test function, that's going to be phi. If it's 0 outside this region, I'm not going to have to worry about that. Okay, so now we just have to write that out algebraically. Okay, oh yeah, and so, well, let's make it more explicit. Phi, in purple, is going to be the row function, the smooth rectangle function. It's going to turn on at x naught minus delta, but then, well, start turning on there and be fully turned on at x naught minus delta over 2, and then start turning off at x naught plus delta over 2 and be fully turned off at x naught plus delta. Okay. So now the integral of f of x, phi of x, this is what I wanted to show was not zero. I wanted to show that if you're not zero as an ordinary function, there's some test function, some thermometer that verifies you are not zero as a distribution. Okay, so first of all, just the fact that it's supported between x naught minus delta and x naught plus delta changes the bounds on the integral. And in that region, we have good control of f of x. In particular, it's bigger than or equal to 0. So this is, I know that this function is positive and this function is positive by construction. And so I can just throw away this extra stuff in the turn-on regions and concentrate where I really know what's going on. Because in this region, phi of x is a known quantity. That's equal to 1. Okay? And I know that f of x, everywhere in this region, and certainly in the smaller region, is bigger than or equal to f of x naught over 2, integral over the same limits. It's getting kind of squeezed. Same limits, though. Dx. And finally, that's greater than or equal to, well, it's definitely greater than 0. It's just delta times f of an x naught over 2. So if you want that, it's actually, yeah, which actually equals delta f of x naught over 2. The main thing is it's greater than 0, with no doubt. Okay. So using our smoothed rectangle function and the continuity argument to make sure that f was really non-zero on a decent interval, not just at a point, we have got that test functions are actually faithful witnesses for ordinary, at least continuous functions. Okay. Now that's the main thing. We then want to think about, well, what about piecewise functions, things like that. This story goes further, certainly, when we talk about integrable functions, stuff like that. We'll come back to it. But that's really the main argument. And finally, we can be relatively sure that distributions deserve to be called generalized functions. They faithfully represent continuous functions, and they throw in cool stuff like deltas. We'll finish this handout in the next video.